Hello and welcome to the least interesting video about black holes. I'm Caleb.
And I'm Pierce.
In this video, we'll talk about the concepts required to understand black holes, how black holes form, important events in their lives, and some interesting theoretical scenarios. Before talking about black holes, we need to discuss special and general relativity, which are two of the most important and crucial concepts in talking about black holes.
General relativity and special relativity are extremely important here. They describe how our basic intuitions aren't good enough in describing our universe. The question is, how did we even get to these theories?
Newton intuited gravity, and it was an accepted theory for a while. However, as we advanced, so did our theories. When we continued to think about pushing gravity to the extreme, we failed to describe a lot of the phenomena present in the universe. Einstein had his doubts as well.
Newton's theory becomes false because he believed that gravity only acts as a force, while Einstein's theory of general relativity shows that it is actually the curvature of spacetime as a result of mass and energy. Massive objects cause the fabric of spacetime to bend, which explains planetary orbits and gravitational lensing. Gravitational lensing is why we see light bend around a black hole, as shown in the images from the Event Horizon Telescope. Gravitational lensing forces us to see the backside of these massive objects.
Black holes are regions where space-time becomes so warped that not even light can escape. Once something reaches the event horizon, which is the distance where light can't escape, it can't get back out, ever. Einstein's equations tell us that certain phenomena aren't simultaneous for everyone. Even if I'm entirely sure about some moment in time, others might not agree. If I was sitting in space and I observed Albert Einstein in a rocket ship approaching the speed of light, I would measure his clock running slow, and the length of the ship would appear shorter than it actually is. This is a direct effect of general relativity.
Let's focus on some of the most crucial implementations of Einstein's theories when it comes to black holes. Einstein had two postulates with his first theory of special relativity. Light must remain constant, and the laws of physics must be the same for everyone, no matter their state of motion. Since light must remain at the same speed as it falls into a gravitational well, such as our favorite black holes, it must lose energy to keep the speed the same, assuming we were the ones observing the infalling light. This redshift effect is what causes the time discrepancy in black holes relative to an outside observer.
Massive stars that run out of their nuclear fuel, roughly 20 times the mass of our own sun or greater, eventually succumb to the geometry of spacetime and collapse under their own weight. This typically creates a huge supernova. However, recent studies suggest that black holes above 17 solar masses can undergo a silent death, one that does not result in supernova. This extreme amount of mass creates the well in spacetime that we refer to as black holes.
This is a fairly common occurrence in nature, as almost every galaxy that we know of contains a black hole at its center. These are called supermassive black holes. While there are only 1 to 2 of these supermassive black holes per galaxy, there are about 10 million to a billion stellar mass black holes in each galaxy.
Black holes behave like huge wells in spacetime and are accompanied by accretion disks when they are active. Non accreting black holes are called dormant black holes. For example, one of the most famous films, Interstellar, portrays an active supermassive black hole with an accretion disk. The animations used for this are directly referencing Einstein's equations in simulation.
It's a common misconception to think that black holes suck things in, and this is an entirely false line of reasoning. There is no mechanism that would support a suction of material. Rather, when material such as gas gets too close to the event horizon, it falls in and is not sucked into the center of black holes.
After black holes form, they remain relatively uneventful for most of their lives. We'll take the opportunity here to explore the nature of black holes firsthand according to Einstein's general relativity, along with some imagination.
So then what might happen if you fall in? Here we need to outline two separate cases, non-rotating black holes and rotating black holes. In this, we'll only consider supermassive black holes, as falling into a stellar mass black hole, rotating or non-rotating, would be instant death due to the extreme gravitational gradient that is present near the black hole, commonly known as spaghettification. This event is lessened as the black hole increases in size, and the severity of spaghettification at the event horizon becomes unnoticeable.
For a non rotating black hole, if the black hole is large enough, you fall in without even noticing. The gravitational gradient is not high enough for you to feel its effects. Falling in would be seamless until you approach the singularity. Here, the spaghettification effect grows without bound until you're torn apart.
For a rotating black hole, however, something strange happens. Spacetime is literally being dragged around. You'll still follow its path. Crossing the event horizon would be the same as before, seamless. However, as you reach the black hole's center, you'll cross another horizon known as the Cauchy horizon. Since you fall with the rotation of the black hole, there are theoretical paths such that you'll entirely miss the singularity and actually survive the black hole's grasp. There are even theories of traveling to other spaces in time, or even other universes, all supported by theoretical solutions to Einstein's general relativity equations.
An important event in a black hole's life is a possible merger. Black hole mergers have helped us understand more about the universe because of what happens when they merge. Black holes in a binary system will slowly approach each other because of their immense masses, and once they do, they will have an extremely high energy collision. Before they merge, however, the black holes go through a stage called inspiral, where the angular momentum increases their velocities. During this time, ripples in spacetime called gravitational waves are released. This phenomenon is predicted in Einstein's theory of general relativity. This is because a few percent of the mass is directly converted into energy, and these waves carry energy away. Once they finally merge, the two black holes will form a larger black hole. At first, the new black hole is unstable and vibrates. These vibrations also cause gravitational waves to be emitted. This stage is called the ring down.
One of the most perplexing parts of black holes is how they die. Technically, they aren't dying. Black holes aren't completely dark. A special type of radiation called Hawking radiation is emitted by the black hole because of particle-antiparticle pairs. This seems counterintuitive because nothing is supposed to escape a black hole, but this is explained through quantum field theory. This happens on an extremely slow timescale, with the death of a stellar mass black hole taking about 10 to the 67 years to fully evaporate.